yourself. I'm Joel Zook. I work for the Winnebago Energy District, and Jolene Jansen and I have been working on this project through the city to help the city and the user group keep the district energy system going and looking at plans for expansion and growth into the future.
Yeah, I've been in geothermal industry, specifically low-grade ground source heat pump geothermal since the late 90s. Was heavily involved in the residential sector for most of my career up until about maybe 7-8 years ago, and then started getting heavier into the commercial side of the business in the last 4 years, working for MVP Saul O'Brien as the director of geothermal operations, and been heavily involved in the last couple of years in just district systems. There's very large interest across the nation and in Canada about district geothermal opportunities. How do these systems, how can you implement these systems on a wider scale? How can it serve residential communities, multifamily communities, and then indeed even commercial communities like we have here at West Union. Oftentimes it is confusing about, how do I save money with this technology when I'm switching from, maybe a fossil fuel type system, natural gas or propane, to an all electric heat pump system. Well, the heat pump actually intensifies energy, and that's the whole premise of how it works. So if you had a electric resistance heat, you have a 1-to-1 ratio of energy in to energy out. And again, we're going to talk about energy and not dollars. So utility costs always play into, how much you're going to save on your utilities. But as far as energy is concerned, if you look just straight at energy itself, a geothermal heat pump moves energy. It doesn't create it. So a gas furnace would be creating energy through combustion. So you're taking a fuel and burning it and creating that, and then you have some waste. So you can never get to 100% efficiency because you always have something going up the chimney or out the flue. With a geothermal heat pump, we're not creating energy, we're just simply moving it. We're moving that through temperature differentials. So we have a hot side and a cold side. When the ground is cooler, we can move that energy into the building, intensify that through the heat pump and the compression cycle, and then you have energy into the building. And you do that all at 3 to 4 times the efficiency, or what some would call 300 or 400% efficiency, comparative to a gas furnace that would be less than 100%. So for every dollar, for instance, if you were just to break it down, for every dollar you put into a furnace, you might get 80 or 90 cents worth of energy out of it. For a geothermal heat pump, you put in $1, you're getting $3 to $4 worth of energy out of it, because you're moving energy that's there in the ground into the building and just intensifying it. You're not creating, if you look at natural gas prices, especially in that region, you're still at almost historic lows since, the last 3 or 4 years. Obviously, you're not going to stay at historic lows forever. But even at historic lows and at electric prices where they're at today, you're still on the winning side because of that advantage of being 300 or 400% efficient in heating. You're also much more efficient in cooling. We're dealing with much cooler ground temperatures than you are if you had a condensing unit sitting outside in 85, 95 degree air. So when you add in cooling and you add in the efficiency of the heating, you're still on the winning side. So you're, on average, you can be saving anywhere from maybe a smaller user in some of the retail spaces of maybe $500 a year. And we've seen some of the larger users up over a couple $1,000s a year in savings at today's energy rates. We came in, as part of this project to do the analysis of an existing system. So we did not do the original design. So, we didn't have any biases to whether or not we thought it worked or not. So we were really looking at it from a clean slate. And so we've got all the documentation. We've done a complete analysis from everything to a hydraulic analysis and whether or not the pumps are sufficient, the way that the piping was laid out, the number of bores or loops that are in the first phase to generate enough energy to support what's connected to the system today. And then, of course, we looked at resiliency. We looked at the longevity of the system. We analyzed 4 or 5 of the different buildings to look at the energy use and how that was all working together. And from our perspective, the system is working very well. It's a very healthy system. And how did we determine that? Well, the first thing about geothermal systems that you need to understand is it's all about the temperature of the water that's being supplied to the heat pumps. So inside the building, you have the heat pumps, and the warmer that water in the wintertime and the cooler that water in the summertime, the more efficient the systems. And so as an engineer, all the systems that we've designed over the years, we generally would design around maybe 35-degree minimum temperature in the heating season and maybe 85 degrees maximum in the cooling season. And as we analyze this system and we look back and talk to the field service contractor, we tried to get some trend data of some of the controls that were monitoring this. And the temperatures in the wintertime never drop below 43, 44 degrees, and they don't ever get above around 72 to 74 degrees in the summer. So you have effectively a 10-degree buffer on the low end and a 10-degree buffer on the high end. That suggests you have a lot of extra capacity, and which also suggests that the system is running very efficient. And what we attribute that to is really all the additional piping that probably wasn't taken into consideration in the initial design that goes throughout all the streets. Because every lineal foot of pipe actually transfers energy. If you have a delta T to the earth from inside the fluid, you're going to move energy. And so all that piping network also acts as a heat exchange. And so we've got extra.
So it's kind of like the distribution system is its own little set of wells, in addition to the wells that are in the courthouse lawn.
Absolutely correct. So that tells us we have extra capacity. We know that the system's working very well. We know the system's efficient. To what degree? We've basically analyzed, you have roughly around 75 extra tons of capacity, heating capacity that you could add to the system before you would start to get below that threshold on the low end, that I mentioned, the 35 degrees. Now, it could be more than that, it could be less than that. We don't know for sure unless we had full, energy profiles of every building that was going to be connected and did a little more intricate analysis of all that lateral piping or distribution piping. But and the best way to really do that, we'll get to that later, I think, is just do more monitoring and more trending as you go forward to really get a better idea of what's happening in the system. And you can then predict what's going to happen in the future as you add more buildings and more users. So, but from a health perspective, back to the resiliency of the system, you've got redundant pumps in the courthouse that if anything were to go down, another pump would come back, online right away. It's sitting there idling basically. And so you've got resiliency built in or redundancy built in that manner. All the piping underground is made of high density polyethylene plastic, which is theoretical life over 200 years. Every other industry that uses the same material for their infrastructure, like sewer, water, gas, has an 80-year life asset as a utility provider. So that the system's going to be there for the long haul. All the joints underground are heat fused. There's no mechanical joints unless they're accessible, which is either in a vault or a manhole. Otherwise, everything is heat fused, which basically is as strong as the pipe, or maybe the pipe expands and it uses a little bit of fluid. You've got that there and it's ready to keep the system pressurized and keep it running. So from a design standpoint, from a technical standpoint, the resiliency and the health of the system is really good from our perspective. A few recommendations that we had, and you'll see in our final report, is that first of all, some better monitoring would really be beneficial to the user group, because they can really see how the system is reacting, how much more capacity they have. And to how to do that is you have to, number one, there's a few sensors that are not operable currently. So we do not have any trend data, and we're not logging any of that data currently to see what the temperatures are over time. So fix those sensors, trend that data, and put that data into a database that you can go back and monitor, actually review and look at. The other thing that we looked at was the hydraulic function of the system. What that means is the pumping. So how do we pump all the fluid through the system? And right now, currently, there's one pump that pumps the entire system through the ground loop, into the courthouse, out of the courthouse, down the street, and the connection to all the other buildings. What we would suggest, just to increase efficiency, decrease the pumping power, would be to isolate those two or decouple them and have one pump specifically for the ground loop and then another pump specifically for the distribution network of piping. The reason why you do that is as more buildings are using in the fall and the spring, some might be in heating, some might be in cooling, you're pumping all that fluid through the street. You don't necessarily need to have the same flow through the ground loop because you have an energy balance going on just in the distribution network. So you can cut that horsepower, which increases your efficiency and your operating costs. But that would require, obviously cutting the system open, putting in a decoupling device, another set of pumps. That would probably be best suited if the system was ever expanded. If Lions Park ever came on and enough users came on that we needed more capacity, that would be a good time then to review that, because you're going to have to do some of that work anyway with additional fluid, flushing and filling again and all that. So that would be a good time to do that. And then just the control platform, being able to operate the pumps in a manner that adjusts the speed based on the needs. Right now, everything is being run manually, which isn't the end of the world. It's not a huge dollar savings because you're only running one set of pumps, and it's not a real big deal. But again, if we're trying to get everything we can out of a system, it really needs to be controlled based on the temperatures in an automated control platform, which was the original intent. But when the sensor failed, they had to go to a manual system, and so that just needs to get repaired, reprogrammed, and then that'll be back up and running. That goes back to the monthly fees that they're paying, and what that construction cost would be to add Lions Park, and then how many more users then can you bring on board at that time to maximize the return on investment of your capital expenditure to put that in. So Lions Park is also about I believe about the same size as the current system, so you'd be almost doubling the current capacity. So right now there's 14 users. You could probably go to 17 or 18 users depending on the size of that user and what type of user they are. Are they a retail store with a lot of heating needs, or are they more of a commercial space that has a lot of cooling needs? Because that helps offset, you could have some simultaneous or coincidental load that help each other, and you don't need a bore field for that. So a lot of things go into that answer, but primarily it's you look at each user. You can expand right now slightly to add a few more users, but then to add Lions Park, it's another big capital expenditure. You'd want to add quite a few more users then to keep your user group per ton cost down where it is now or lower. Versus if you added all that for extra capacity, didn't get the users, now your costs would be higher. So the key is to have enough users to come on to use that capacity.